So welcome everybody. This is the final PhD exam for Roland Farrell. Roland Farrell's advisor of Science Beam is online, but I'll be emceeing today. Roland is working with the Nuclear Theory Group. He's done a number of really interesting projects in the area of fundamental science related to the structure of matter, both in nuclear theory and also recently in the last year and a half or so on quantum simulation and quantum computing, again addressing the same physics problems with a new emerging technique. So the format of the discussion today is we'll have a presentation for about 40-45 minutes, followed by open questions, and then we'll go into the closed session with questions from the committee and so forth. A particular note is that Roland's one of our own in the sense that he grew up in Mount Vernon. I believe parents are here, even though I haven't met you yet. Right? Yeah. And then was an undergraduate here at the University of Washington and then into the PhD program. So it makes him somewhat unique in this regard. Roland, take it away. It's yours.
Yeah. Thank you for the introduction. Yeah, I've been at UW for 10 years, so definitely the end of an era. Yeah, thank you all for coming to my defense. Very excited to tell you about the work that I've been doing during my PhD. So, like Martin mentioned, I've had a really great opportunity to work on a number of different projects across different domains. When I started out, I was working with Silas, and we were looking at entanglement produced in scattering events with neutrons and other hadrons, and we were investigating kind of a conjecture that entanglement is suppressed in these kind of scattering events. And we started looking at this kind of geometric understanding of entanglement, and this motivated a new way to look at the low energy interactions between neutrons and protons. And we found that there's this new kind of symmetry, a UV-IR symmetry, that relates scattering at low energies and high energies. So in a series of papers, we investigated how this manifests and the consequences of this, and what are the implications for nuclear physics. That was that paper there. And we found that it kind of motivates a new way of organizing hierarchies in nuclear forces. And then I've also been able to work on doing calculations for quantum gases. So these are very cold gases of fermions that are interacting, and we've looked at doing systematic calculations of their energy density and also superfluid properties. And then most recently with Martin and other people in this room and in the incubator for quantum simulation, I've been working on doing quantum simulation of lattice gauge theories to really start to look if we can solve standard model questions on quantum computers. And this has been great because we've really kind of started in close to ground zero. So we've been building in a new framework for how you're going to do this for many years to come. So it's been a very exciting time. And this is mostly what I'll focus about during the talk today. I can try. Good. Yeah. So to begin with, I want to start by just posing what are the big motivating questions that ultimately I want to answer and other scientists want to answer. One of them is, what is the composition of matter at very high densities? So as kind of a warm-up, a more familiar example is in the case with water, where we know that if we tweak external parameters such as the pressure or the temperature, we can have it go through various phases. So what's shown here is you start with some gaseous phase at lower pressure, and if you keep squeezing the molecules together, you can transition to a water and ice phase, liquid and ice phase. This is showing that as you vary this pressure knob, you can probe different types of matter. But as someone with a nuclear physics background, I'm interested in what's the composition of matter at extremely high densities, at nuclear densities. So here you have a similar kind of thing going on, where at lower densities, you have a gas of atoms. So you have neutrons and protons, and they have their cloud of electrons around them. These are kind of what you would find in the periodic table. But then as you squeeze these things closer together, eventually you enter a regime where you don't really have electrons anymore because you have Coulomb repulsion, and you mostly have a state of matter composed primarily of neutrons. And if you squeeze it even further still, then what's relevant is not these neutrons and protons, but the quarks and the gluons that are inside them. And in fact, we don't really know what type of matter we get if we squeeze things and go to really high densities. And so this is kind of encapsulated in the phase diagram of quantum chromodynamics shown up here, where as a function of density, you go from low density where you have neutrons or nuclei. As you go to larger and larger density, eventually you reach the regime relevant to neutron stars. So neutron stars are big astrophysical objects, mostly composed of neutrons. And if you look close into the core of the neutron star, you find extremely dense matter, the type that we don't really know what's going on. So this is one of the fundamental questions that we would like to be able to answer. Another one is looking at what happens during high energy collisions between nuclei. So the kind of flagship example of this is a sort of experiment you would have at the LHC, where you have a big collider that's about 20 miles in circumference, and you're accelerating nuclei, in this case, lead nuclei, close to the speed of light, and you smash them together at really high speeds, and you see what happens. And well, what happens is, if it's very high energies, then these neutrons and protons explode, and you just get what's called this quark-gluon plasma. So what's relevant is the quarks and the gluons inside of the neutrons and protons. And this is some strongly correlated liquid, which then, as it expands and cools, eventually forms back into nuclei and other particles that you measure in your detectors. But in our experiment, what we have access to is our initial state. We know which nuclei we're colliding together. We have our final state. We know what happens in our detector. But we have a lot of inference for what's going on in this intermediate region. How do we go from having protons and neutrons to quarks and gluons? And how do we go back into neutrons and protons? These are all kind of open questions, and they're hard questions. So yeah, one of the things that I want to address is people have been thinking about these kind of things for a long time. The reason why they're still more or less unsolved is because they're extremely difficult questions. So why is now a good time to be looking at them? And from my point of view, there's two reasons. One is because we're entering kind of a new regime of astrophysics or astronomy, the era of multi-messenger astronomy. So historically, we've had access to astronomical observations in the electromagnetic regime, so radio waves or X-rays or visible light. But since 2015, when LIGO detected the first black hole merger, we've been able to see gravitational wave signatures. And so the idea is that you have two very compact objects like neutron stars or black holes, and when they merge together, you can they send out some gravitational waves, which remarkably, even though these are very far away, you can actually detect here on Earth. And one of these detectors is in Hanford in Eastern Washington, so pretty close. But what's exciting about this is that these are the kinds of objects which have these very dense phases of matter, which we don't really know the composition of. And so these sort of measurements can tell us what's going on there. So that's one reason. Unfortunately, I don't work on gravitational wave astronomy, but it's very exciting. The other one for me is quantum computing. So we're really kind of at ground zero of quantum computers. The first ones are just coming online in the last 5 or maybe 10 years. And this is giving a paradigm shift of what's possible to do with computing. In particular, what kind of situations can we simulate with our computers? And so this is the area that I've been working on and what I'll be talking about for the rest of this talk. So to provide some background and motivate how we could even go about solving these kinds of problems using quantum computers, I want to briefly introduce the standard model. So the standard model of particle physics describes the fundamental particles. You have the quarks up here, the leptons, these are the gauge bosons, and that's the Higgs boson. It's a very small catalog of particles, but the standard model tells you what they are and how they interact. And in principle, kind of all the matter that we know about is composed of these different particles. So in particular, neutron stars are composed of these particles, and when we smash nuclei together, what we have, the quarks and gluons, are described by the Standard Model. And we have a set of equations that tells us what in principle happens during these situations. And so all we need to do is solve these equations. But of course, this is extremely naive. These equations are very difficult to solve in a lot of cases. In particular, when we have systems of nuclei. So when we have neutrons and protons, this involves the strong nuclear force, or quantum chromodynamics, so the quarks and the gluons. And this is a nice picture from Brookhaven National Lab, kind of showing an artistic rendition of the proton, where you have the proton, and inside it you have quarks of different colors and gluons, and they're all wrapped up in some confined bound state. And so you can imagine trying to calculate how that emerges from quarks and gluons is quite difficult. But the way forward, which was realized, I think almost 50 years ago, was that we can put the Standard Model physics onto what's called the lattice. So the lattice, we take some space-time volume, which is continuous. We have continuous space and continuous time. And then we discretize it with a lattice of points to form some kind of grid-like structure like that. And this becomes something that you can put on a quantum computer, or sorry, a regular computer. And then the idea is that your Standard Model particles exist on the lattice points, and this gives you some computational framework to begin solving what happens if you have systems of Standard Model particles. So this has been done historically using the largest classical supercomputers we have available. And it turns out that doing this technique with Monte Carlo sampling, where you're essentially sampling different particle configurations on your lattice, you're able to efficiently compute static properties and properties of dilute matter. So matter that's not dense and not changing in time. And this has had some really great successes over the last 20 years, and I just want to highlight a couple of them. One is from the BMW group, which is not the car company, but a collaboration in Europe. This is from 2008. And it's showing that they did a lattice calculation where they, as input, put in the masses of 3 different hadrons. And they were able to predict the masses of a slew of other hadrons, these red dots. And you can see that within error bars, these agree with the experimental determined values of the masses. And in some case, the theoretical uncertainty is even lower than the experimental uncertainty. This shows that kind of all these systematic uncertainties are well understood, and this framework of lattice QCD can really reproduce nature. A second example is from the NPL QCD group, of which there's some founding members in the audience. And one of the things that they were able to do is deduce scattering parameters directly from lattice QCD. So looking at scattering between nucleons or hypernucleons, they're able to extract scattering lengths and effective ranges. And these kind of tell you about scattering processes between these particles. So lattice QCD has been enormously successful, but it has its drawbacks. In particular, dynamics, when the system is changing in time, or dense system where you have a lot of particles together, these become intractable using classical computers. And what this means is that if you set up some simulation, you could wait a really long time and you still wouldn't have an answer for what is the composition of dense matter, what happens in a dynamical process. But one of the great things which was realized, also almost 50 years ago by Richard Feynman and other pioneers, is that these kinds of simulations are believed to be efficient using quantum computers. And so this motivates a lot of the work that I've been doing. So to just briefly set the stage, I want to compare and contrast classical computers and quantum computers. So with a classical computer, you have states that are represented by zeros and ones. And physically, these are, you can think of them as charges on a capacitor. A 1 is if the capacitor is charged, a 0 is if the capacitor is uncharged. And then what you do with a classical computer is you connect the capacitor with wires to your CPU, which is a bunch of transistors. These transistors perform some kind of logical operation. And depending on your initial zeros and ones, you can spit out a different set of zeros and ones. Okay, but quantum computer operates a little bit differently. Instead of having these capacitors storing your state, you have some kind of physical quantum system. So you could think of it as being energy levels of an atom. And usually we think of it as being two energy levels. So you could have the low energy state and high energy state. So low energy state would be the 0, the high energy state would be the 1. And what's different in quantum mechanics is you're not kind of constrained to be in just one state or the other state, but you can have this so-called quantum superposition. And so the state of your quantum computer can be kind of this superposition of this 0, 1, 1 state and this 0, 0, 1 state. And then the same kind of thing applies. You can apply some physical process to change the state. You can think of this as being lasers that excite you between the low energy state and the high energy state. And this could modify the state on your quantum computer and give you a different superposition. And so it turns out this ability to have states in superposition, which you can modify extremely well with some kind of lasers or other type of physical process, allows you to do computing tasks which are much more efficient than with classical computers. And before we go any further, I just want to introduce some notation that I'll use in the rest of the talk. So the first one is this idea of a qubit. So I said that you can think of the kind of fundamental piece of memory or your state as being this low energy state of an atom or a high energy state of an atom. But in principle, it could be something more generic. And we usually just think of this as a generic two-level quantum state that we represent as this little sphere with an arrow, where the arrow is telling you what state it's in. The other idea is the idea of a circuit. So when we're doing some operations on our qubits, we usually represent that with a circuit diagram shown over here. So here, time is kind of going from left to right. Each one of these horizontal lines represents the state of a qubit. And then you have these gates. This is a 2-qubit gate. This is a 1-qubit gate that are acting on the qubits. They change the state, and this whole thing forms a circuit. The details of this are not too important, but one of the things that I want to stress is that if you have more gates than on the quantum computers we have today, this leads to more noise and more errors in your computation. So kind of the name of the game is you want to reduce the gates as much as possible. Okay, so before I introduce lattice as being this 3D or even 4D structure, but my research is focused on doing dynamical processes in one dimension. So instead of a 3D lattice, on 1D, we just have a line of lattice points, and our quarks in this case would live on the different lattice points. And the way this gets mapped onto the quantum computer is you take the states of the quarks and you map them onto the states of the qubits. So yeah, not too complicated, but from a high level, that's how we do it. And these 1D systems are very popular because they have a lot of simplifications over the full 3D systems. And so a lot of people from many different groups have been using this to develop these quantum simulation techniques. There's groups in Canada, Maryland, Europe. It's the whole kind of international endeavor to develop these quantum simulation, and really starting with the 1D systems that are the simplest before we expand onto the more higher dimensional systems that more mimic nature. So in this slide, I just want to show kind of a cartoon of what we do in a quantum simulation. So a prototypical example would be that at time 0, we have 2 nuclei kind of at rest here, and we want to simulate some kind of collision. So we increment time forward, the nuclei move towards each other and collide. That's kind of our goal simulation. On the quantum computer, this breaks down into 2 parts. First, we have some circuit that prepares our initial state. So in this case, these 2 nuclei that are far apart. And then we have circuits that move us forward a little bit in time. This is called time evolution. And what we do is we keep adding on more and more of these time evolution circuits to build out our full simulation. And then at the end, what we do is we measure the state on the quantum computer. And from those measurements, we deduce some interesting observables. in some collision process like this, it could be the particle content that's produced after the collision. In my work, I've worked on techniques and algorithms for both doing the state preparation part and also the time evolution part. For the sake of this talk, I'm just going to focus on the state preparation, and I'll be presenting results where we do both the state preparation and the time evolution. So one of the big breakthroughs that we had was developing this technique called Scalable Circuits Adapt VQE, or SC Adapt VQE for short. This is for preparing states on a quantum computer. This builds off of Adapt VQE, which is a quantum computing algorithm that was developed for chemistry out of scientists from Virginia Tech. And so we kind of change this algorithm for our own purposes. And from a high level, this is how it works. So on a classical computer, we run this Adapt VQE algorithm, which is a variational algorithm for determining circuits that prepare some state on a quantum computer. And what we put in is we put in the physics of the system that we're interested in. So in particular, the symmetries and hierarchies of length scale that are present in our system, we use to constrain what kind of circuits we're looking for that can prepare our state. And this is all done on classical computers, which can look at states up to some finite number of qubits, usually about 30 before you run out of memory on your computer. And then the scalable part is that you scale these state preparation circuits, which can then be executed on a quantum computer. So the idea is that you find these circuits on small systems using a classical computer, then you have some technique for robustly scaling them up to a size which you can no longer run on a classical computer, and these are run on a quantum computer. So this is showing some IBM quantum chip, and you have some large circuit that you're trying to run on that. Okay, and so I want to give a little bit more of the physics intuition for how this algorithm works. And I want to do that by presenting one application of it, which is for preparing the vacuum or the ground state of your system, the state with lowest energy. So as I said, the symmetries of the system are very important. For us, these often have translational symmetry. What this means is that if I look at the state on one part of my lattice, or the state of the qubits on one part of my register, it's going to look the same if I also look at a different part, because these are just related by shifting across the lattice. And this has important implications for the circuits that would prepare such a state with translational symmetry. In particular, I could consider constructing the vacuum, and I know that I would need to preserve this translational symmetry, which means that these circuit elements must be repeated across the lattice. This is shown here. This little red box is some 1 qubit circuit element, which is repeated across the whole lattice. This green one is some 2 qubit operation repeated across the whole lattice. And you can imagine that if you had enough of these, you'd be able to prepare the vacuum state exactly. So that already tremendously constrains kind of the search space for what kind of circuits could be preparing our vacuum state. Okay, another feature of the systems that we're often interested in is that they don't have massless particles. We're usually interested in lattice gauge theories, which have what's called a mass gap. And so there's a separation between the ground state and the first excited state. Yeah, it means there's no massless particles. And what this means is a little bit more nuanced, but it essentially means that if I look at the state at 2 faraway regions on the lattice, that the state is approximately independent of each other. So you have this kind of factorization where the state on, say, the left side and the right side is approximately equal to whatever you would find on the right side times whatever you would find on the left side. And this has a couple of implications for the circuits. The first one is that we don't need long-range circuits in our state preparation onslaughts. So before I had this orange one that spanned 4 qubits, you can think of this circuit element as building correlations that are across 4 different sites. But because we have this factorization, we would expect this to factorize, say, into correlations across 2 sites. And so to very good approximation, you could just drop those and just build out the correlations on a smaller subset. this has another implication, which is that these circuit elements that we find, these 1, 2, and 3 qubit boxes, are approximately independent of system size. This is because you can think of, in order for the state here to know that it's in a finite size volume, it would need to be able to talk to the state on kind of the other side to know that it's not an infinite size volume. But if these are independent of each other, then it essentially doesn't know that. So yeah, this is kind of the physics that goes into the scalable circuits at DAFT-VQE. Now I want to present a couple of examples where we've used this method to prepare our initial state and present the results from a couple of simulations that we've done. So the first one is for a quantum simulation of neutrinoless double beta decay. So to kind of set the stage, some atoms are unstable to double beta decay. So the prototypical example is germanium-76 can decay to selenium-76 while giving off 2 electrons and 2 antineutrinos. And this has garnered a lot of interest recently for the following reason, that the neutrinos, this particle here, they have a mass which is not actually explained by the standard model. It's some beyond the standard model mechanism that's giving them a mass. And a very popular explanation is what's called this Majorana mass mechanism. And the reason this is important is that once you have a Majorana mass, you have this new kind of decay process that opens up, which is called neutrinoless double beta decay. So it's a decay where you only have the, say, selenium-76 and the electrons in your final state. You don't have any neutrinos. And so it's been a big experimental endeavor across many different collaborations. This is the LEGEND detector that's trying to detect this decay process in germanium-76 to kind of see if such a decay process can actually happen. Now, the way the simulations come into play is that you can imagine that if this experiment were to detect some neutrinoless double beta decay event, you would ideally want to be able to reverse that into a prediction for what is the Majorana mass of the neutrino. But it turns out that that's kind of a very difficult inverse problem to solve. And it's one area where having simulations directly from the standard model can inform you what's going on. So we've just been working in one dimension where beta decay and double beta decay looks a little bit different. In particular, our decay process looks like a delta minus goes to delta zero plus 2 electrons. These states have isospin 3 halves, and you can think of this one as kind of being like a neutron and this one kind of being like a proton. It's just some quirk of working in one dimension. So then the simulation that we're performing is, first, we use this SC ADAPT-VQE technique to prepare our delta minus initial state. And then we evolve it forward in time and we see, okay, are we having any decay or not? So this is shown here. We're adding in more and more time evolution. Our initial delta minus state is disappearing, getting replaced by the delta zero state of the electrons. And we expect that if we evolve for long enough in time, it would fully decay. And so then at the end of this simulation, we measure what's the probability we had this neutrinoless double beta decay event. So this whole idea is building off of work that we did in September of 2022 using Quantinuum's quantum computers. So there we looked at a simulation not of double beta decay, but of single beta decay. And we did it on one lattice site with 2 flavors of quarks and 2 flavors of leptons. And this system mapped onto 16 qubits and took 212 of these gates in order to perform. And so what you see here is, as a function of time, we're able to extract what's the beta decay probability. And because this is a relatively small system, we have an exact prediction, this dashed black line. We have the results from the quantum computer, these blue circles, which for the most part are within statistical uncertainty of our exact prediction. And then these orange and green ones are from classical simulations of the quantum computer. So this kind of developed the framework for doing these simulations of beta decays. Second example, and the last one that I wanted to present, is a simulation that we did of hadron dynamics. So a hadron is a composite bound state in QCD. So a proton is a hadron because it's composed of these quarks and gluons. And we wanted to simulate some dynamical process. So again, we start at time t equals 0 with a hadron at rest in the middle of the lattice. We use this scalable circuits adapt VQE to prepare this initial state. And then we evolve it forward in time. And because our initial state had an equal probability to travel left as it does to travel right, it kind of spreads out from the center and moves out across the lattice. And then after the simulation, what we want to measure is kind of where is the position of the hadron as a function of time. So these are the results that we obtained. This is work that we put out back in January of this year. So this is showing as a function of lattice height. We did this on a 112 qubit lattice in time going from 0 to 14. And this color is showing you where is kind of the probability of finding the hadron. You can see at time t equals 0, we have it very well localized here in the center of our lattice. And then as we evolve outwards, there's kind of this two branching paths for it to go left or to go right. And what this plot actually shows is on like the right half of this lattice is the results from the quantum computer, IBM Torino. On the left half is the results from using a classical tensor network approximation, which we expect to be quite well converged and to be the answer if there was no noise on the quantum computer. So if there's no noise, we expect this figure to be perfectly reflection symmetric. But you can see that there is some noise, some errors that breaks this reflection symmetry. But for the most part, this signature of a hadron propagating outwards is clearly identifiable. This is kind of the first ingredient to begin simulating collisions where you could have multiple hadrons moving and then colliding with each other. And I want to emphasize that at the time, this was kind of the largest quantum simulation that had been performed on a device. To go to this latest time of time equals 14, we used 13,858 gates, and we did 154 million shots over this whole production. So we ran 154 million circuits on the quantum computer. And I want to emphasize with this slide that these quantum computers are noisy, and these error mitigation techniques are essential if you want to actually get results from the quantum computer. So I'll bring your attention to this panel up here in the top left. This is showing the raw results from the quantum computer. And the little circles are what we got off the quantum computer. The black lines are our expectations. And for the most part, it's just a completely flat line. There's kind of no signature of anything going on. If you looked at it, you would say that the device has decohered and there's kind of no information left. It just looks like garbage. But in fact, because we did 154 million runs of garbage, you're able to extract physics, which is what's shown in this bottom right. So after carefully analyzing the different runs, you can extract a signal from seemingly no signal. And that's what's shown down here, where this little bump is showing kind of the hadron, which has moved a little bit to the right, and also some probability for it to have moved to the left. So with that, I would like to wrap up with a brief outlook. So when I started doing the quantum simulations, we were using devices that had 6 qubits, and we could do 34 gates. This is back in July of 2022. This was really pushing the capability of the device. We had to work hard to get anything useful off of these relatively small circuits. But then already in September of that year, we were doing circuits with 17 qubits and 212 gates. And then in August of 2023, we were doing 100 qubits and over 2,000 gates. And then this result from January, we're doing 112 qubits with close to 14,000 gates. So I've seen a lot of very nonlinear growth in the capabilities of these quantum computers. And I'm very excited for the future to see what the community is going to be able to simulate. And I think within the next 3-ish years, we'll be able to make kind of impactful statements about aspects of standard model physics and just other dynamical questions that are hard to address. So with that, I would like to thank all of my collaborators and my group members and also the people that have provided funding for my research. And thank you all for listening, and I'd be happy to take any questions.
Yeah, so questions for Rob? Yeah.
What's like the physical distance between two ladder sets?
Yeah, so this actually is kind of tied into Larry's question. So the relevant length scales in this case are what's the size of your particles, in this case, the hadrons. So for instance, in this simulation here, our hadrons were very well localized. They spanned about one lattice site. So each lattice site was about the size of one hadron. And that's kind of the relevant length scale. In real world terms, I'd have to get back to you. Like physically on the quantum computer, or? Yeah, we didn't match it onto any kind of known thing, so yeah.
Yeah. No.
You know, presumably the next step is going to two dimensions. So what exactly do you see as the bigger challenges across the case?
Yeah, really good question. There's kind of a number of challenges, both on like the theoretical front and the quantum hardware front. On the theoretical front, in one dimension, we have a nice simplification where we have these gluons or these gauge bosons, which we don't actually need to include in our simulation because their dynamics are completely constrained by what our fermions are doing. But once you go to two dimensions, that's no longer true. You need to include them in your simulation, and this becomes a lot more challenging because you have more kind of degrees of freedom that you need to juggle. Another difficulty is that taking your fermions, your quarks, and mapping them onto states of qubits becomes a lot more difficult in two dimensions relative to one dimension. So that's another challenge. And then the hardware challenge is that in 2D, you'd like to have some kind of 2D connectivity between qubits in order to efficiently map your system onto the quantum computer. But devices with these 2D architecture are somewhat more scarce. And so it's a challenge to realize that connectivity.
So the variational approach is like really very powerful for like really getting all the use you can out of the device. What, like, how like relevant do you see it kind of do you see that really relevant to the near term, or do you think like it's going to, you know, kind of different forms of variational techniques are going to stay relevant for a very long time? Like, what do you see the role of the variational techniques?
I think the variational techniques are going to be useful long term, but I think there's going to be a lot of interplay between doing a lot of the optimization on classical supercomputers first to kind of search over the non-entangling quantum circuits, and then only on the quantum computer are you doing that last push into the entangling regime. So really splitting your workload so that the quantum computer is doing the quantum difficult part.
Yes, from a very late perspective, how do you take your theoretical approach and what evidence you have in the real world that what you're doing is just chasing marbles down always? And how do you, you know, what evidence is out there that allows you to suggest that these are actually, you know, real principles?
Yeah, we don't want to be chasing marbles down the hallway. Yeah, for me, like these classical lattice QCD simulations that have been able to really well reproduce the results of nature. So I showed that one plot of this lattice simulation where they fed in a couple of particle masses and were able to predict a few others. That shows that there's very well understood kind of theoretical control over this lattice framework. And so the quantum computing is kind of taking it on another axis, but it's still kind of grounded in that theoretical underpinning that makes it feel like it ties back into reality if you're careful.
So is the world really a lattice or is it just an approximation?
I think the world's really a lattice. But we don't know.
I got another question, one from the lay perspective. When you say 150 million shots, is that 150 million collations of atoms? What does that mean by shots?
Yeah, so when you run on a quantum computer, you take your circuit, you run it on the quantum computer, then you get some output. But because it's quantum mechanics, the output has some different probability of being different states. And so you really need to do a bunch of different runs with the same circuit in order to figure out what's the distribution of the different states. And so 154 million shots, I mean, we ran 154 million different circuits. And from that, we kind of extracted what's the distribution of the states in the that we created.
Any other questions? Yes.
Does the width of the circuit grow the deeper you go? So it's like the chief difficulty gonna be scaling to longer time horizons or?
Yeah. So kind of the picture that I drew was to go further and further in time, you start appending more and more of these circuits, which is getting deeper and deeper and deeper. And that's, yeah, the current limitation is more in that width domain than the length domain.
Very impressive that you run on more than 100 qubits. Now suppose you can have access to the best quantum computer in the world. Then approximately how many qubits and how many gates that you get done now?
Well, the best quantum computer in the world, I don't know, because it's probably very heavily behind a firewall. But the best ones that I know that are available are, I mean, we were pretty much using the very best ones available. So maybe there's like a factor of 2 more in the number of qubits and a factor of 5 more in the number of gates that you could do. But this one, I mean, it was pretty recent, back in January, and it was really when the device kind of first became active. So we've been running on the cutting edge machines.
No questions? Okay, if not, well, thank you again.